This lecture is necessary because the notation that will be used in this course might generate some confusion with the meaning of the symbols. So I want to stress certain concepts in the notation of sets and bases. In the lectures of chapter 9, we will use a notation which may cause some confusion. Reminder: let X be a set with element a square, a triangle, and a star. In mathematics, X is denoted by we open a curly bracket and we list these elements in not a specific order. For example, square, triangle, and star, and then we close the curly bracket. We could have as well indicated the same X by the following string of symbols, open curly bracket, and instead of starting with the square, we can start with a triangle, and then comma, square, and then comma, star. Or starting with the star, and then square, and then triangle. All these notations indicate exactly the same set. There is no particular order on which we list the elements in a set. Just the elements in a set are relevant for the set, not the order in which they are listed. And altogether there are 6 possible ways in which I can denote this set X. In lectures 5.3 and 5.4, we introduced the notion of basis of a vector space V. In particular, as a mathematical object, a basis is just a set of vectors satisfying certain conditions, linear independence and being generators. But as a mathematical object, a basis is just a set of vectors. In lecture 9.4, which is the previous lecture to this one, we define the associated matrix to an homomorphism F as follows. We fix 2 bases, Vj and Wi, the first in the domain and the second in the codomain, and then we compute the kth column of the associated matrix in the following way. So the scalars of this kth column we denote as A1k, A2k, and so on, up to AMk, where m is the dimension of the codomain. And how do we derive these scalars? We take the image of the kth vector of the base of the domain through the map F, and so we are now dealing with a vector in the codomain W, and we express this vector as a linear combination of the bases Vi that we have in the codomain. So Vf of Vk is a linear combination of the vectors Wi with coefficients that we will denote A, I, K. So as you can see, there is a relevance of the order of the vectors in a basis of the domain and the codomain, because the kth column of the associated matrix is computed by looking at the image of the kth vector of the basis of the domain. Remark: if we list the elements of the basis of V in a different order, we will get an associated matrix with its columns permuted accordingly, hence a different matrix. If the kth vector of Vj, the basis V of the domain, is no longer Vk, but it is some other vector, then the kth column of the associated matrix will be computed by using the other vector and no longer Vk. Okay, so let's see a numerical example and see the consequences of permuting vectors in the basis of the domain and the codomain. For instance, let us assume that the associated matrix of F with respect of 2 bases Vj of the domain and Wi of the codomain is the following, with the following columns: A1, A2, A3, B1, B2, B3, and C1, C2, C3. For bases, BV, V1, V2, V3, and BW, W1, W2, W3. If we apply the definition of associated matrix of lecture 9.4 to the basis BV, instead of using V1, V2, V3, we list these bases as V2, V1, V3. As sets, these are exactly the same. This is why I used again the same notation as the basis before. This is exactly the same basis as the one before. You see BV here and BV here. I just inverted the order of the elements in which I have sorted them out. We will get the following associated matrix. It is no longer AF, VJ, VI, VJ, WI, A1, A2, A3, B1, B2, B3, C1, C2, C3, but it will be, the first column will be B1, B2, B3, because the first column here in the matrix, I have to take the first vector of the basis, which is no longer V1, but it is V2, and then take the image by F, and take the linear combination of F of V2 in the codomain with respect of the basis W1, W2, W3. And this is precisely the second column of this matrix. Therefore, switching the first two vectors in the sorting of BV will imply that the associated matrix will have the first two columns that are switched. But this matrix is completely different than this one. And similarly, if you write the matrix associated to V1, V2, V3, and BW, W1, W3, W2, so I'm permuting the second and the third vectors of the basis of the codomain, then what we will get? We will get this new matrix in which we have permuted the second row with the third row. The fact that we are talking about rows and no longer columns is because we have permuted vectors in the codomain. Therefore, what we see is that there is not a well-defined associated matrix to F, BV, and BW unless we fix the order in which we are sorting the vectors of BV and BW. Conclusion: the associated matrix is not well defined from simply the homomorphism F and basis BV and BW. AF VJWI is well defined from F and ordered bases B'V and B'W. Let me denote them with a prime, meaning that they are not simply a set of vectors, but they are a set of vectors endowed with a particular ordering of the vectors. If I change the ordering of the vectors, the set will be the same, but the order set will change because the order has changed. Okay, so B'V is mathematically, if you want, a pair of a set and the ordering of a set. And two pairs are different if one of the two arguments is different. So either I change the elements of the set or I change the ordering on these elements of the set. So once I fix the ordering of the basis, then the associated matrix is well defined. In mathematics, the way to denote a set endowed by a particular order in which the elements are sorted is through the use of round brackets. For instance, if we denote the set that we wrote before of three elements, triangle and square and star, and we write them in round brackets instead of curly brackets, then we are implicitly saying that this is a set of these three elements endowed with this particular order: first the triangle, second the square, and third the star. And if I permute the order of these elements, then the set is exactly the same as before, but the ordering has changed. So round brackets, this listing is different from round brackets and this other listing of elements. And also it's different than round brackets and this other listing of elements and so on. Thus, the correct way of denoting an ordered basis of three vectors is putting them in round brackets instead of curly brackets. However, here is a possible confusion in using this notation, because this notation has been abused. We are using too much round brackets in this course and can be easily confused with many other mathematical objects we are dealing with. However, in this course, round brackets are usually employed for writing ordered sets of scalars, i.e. n tuples in Rn, and the writing v1, v2, v3 in round brackets, or more generally, open a round bracket and write vi and close the round bracket, for vectors vi could be deceiving. In conclusion, in the context of matrices associated to homomorphisms, so bounded in this context, ordered basis will be improperly written as a usual set using curly brackets. So open curly bracket and then write v1 and so on up to vn and close curly bracket. And this is usually the notation of just a set. But in the context of matrices associated to homomorphisms, then this notation will denote an ordered set. So it will mean a set with these elements and in this particular order in which we are writing the vectors. Just like an unordered set, okay? But what we will mean exactly with this notation is the round bracket notation, okay? So the n-tuple of vectors in which the v1 is the first vector, the v2 is the second, so on up to vn. So usual notation for sets will denote ordered sets, okay, while we will be talking about bases to construct associated matrix to homomorphisms. In other contexts, the notation with curly bracket will just be regularly employed for sets. So keep this in mind for the lecture 9.4 and the coming lectures of the chapter 9.